talk is for you. I think today's talk is about explaining some very basic concepts about ZK and what are ZK, what are ZeroKnowledge proofs, and what they are for, and why it works, and why we should learn ZK. And I think for everyone, why should we learn ZK? Okay. I think first of all, we're focusing on the terminology, the jargons. I think when I was beginning to learn ZK stuff, I think the biggest difficulty is about just to learn the jargons, seen by the cryptographers. So first of all, I use my iPad. Okay, let me take a seat. Okay. Is it clear or? Is it clear?
Yeah.
Okay. First, ZK versus ZKP. Okay. Any ideas about ZK? Okay, actually, ZK is an adjective. Okay, now we use that word for noun. Actually, we're talking about, most of the time, we're talking about ZKP, zero-knowledge proofs. So let me write down the whole term. Zero, sorry for my handwriting. Knowledge proof. Okay, what's the difference between ZK and ZKP? Okay, here we can see there is P, right? P is a proof. So think about proof. So what is a proof? Like a mathematical proof? And in the high school or middle school, when teacher asks us to prove something A plus B greater than or equal than A, for example, if A, B are natural numbers. So actually, it's not easy to do that, to prove that. But actually, proof is kind of it's a if a teacher asks us to write a proof, we always like prove like this. So for example, there's a statement or theorem or statement. The cryptographer always mentions, I would say statements instead of theorem. But remember, actually, the two words are exchangeable. Okay, but in the academic paper, we always say the statement. Actually, it's a theorem. This theorem is it's just like a mathematical proof, mathematical theorem. But some differences. We'll talk about that. So then we will write something like that, proof. And blah, 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 blah. We use some lemmas or logical reasoning, then we get QED, right? Saying that, okay, the statement has been proved, so they can convince anybody. So it looks like a decentralized conclusion, right? We don't have to trust any authorities. Okay, this theorem, mathematical theorem, is called one round proof. That I, as a prover, so I write down all the proofs. I write down proof line by line, or the reasoning, the steps, or a tree-like structure, and hand to the teacher. Then teacher, as a verifier, verify each step of reasoning, right? Using the very basic level logic, formal logic, to check if every step is reasonable or not. I think the concept of the proof, originated from the ancient Greek, right? And okay, the history will be in 1985. Yeah. There was a paper published by Goldwasser, Mikhaili, and Rakov, three cryptographers. They come up with idea that extend the concept of proof, saying that okay, there's a proof, there's some new form of proof that we don't have to write down all the reasoning steps, and the proofs contains nothing. Okay, not nothing. Some information, but the verifier cannot extract any useful information from the proof. Okay, it's pretty anti-intuitive, right? So if the proof there's nothing inside, how can it prove some conclusion or a theorem for us? But it proves true. So we have to come up with another proof to prove that the fact that there exists some kind of logic system that we can write the proof without revealing any information about the statement. Sorry, any information except that the statement is true. So that's, I think that okay, in 1985, that year kind of very, very important for not only for cryptography, not only for math, actually for our world to, just revealing some very important philosophical thoughts about the I think nature of the universe or something like that. But the proof kind of different from the variant proof that I mentioned before, the ancient Greek form of proof. Actually, the concept of proof extended to a broader concept, so-called probabilistic proof. Okay, the proof. Okay, here's the math proof. Okay, math proof. Now, here we have sorry for my English. Probabilistic. Is my correct?
Yes.
Okay, yeah, thank you. Probabilistic proof. See that the proof are in the form of interaction. So me as a prover, so I write down something and hand on to the teacher. The teacher, say nothing from the sentence that I wrote. But the teacher can ask me online trying to challenge me about something, about the statement and some information that useful for proving that theorem is true. So after round of interaction, then I was challenged by the teacher of a verifier. So eventually the verifier saying, okay, probably you know that proof of theorem, but I don't know. Because the process of challenging of the interactions don't reveal any useful information why the theorem is true. But the teacher is convinced that I know the proof of theorem. Okay, any question here? Let's stop just for 1 minute. Is that clear so far?
I didn't understand quite the difference between the theorem and the statement.
Okay, they are same.
They're the same. There's no difference. Okay.
Totally interchangeable.
Okay.
And I guess you're saying like a proof, right? You can prove something without revealing all of the data, all the information, right?
Mm-hmm.
And then you talk about probabilistic proof, where you talk about interactiveness.
Yeah.
Is that the difference?
Yeah, differences. Yeah.
Okay.
The proof we will call, for example, we have me as a prover. So I write P here. There's another teacher called verifier. So first of all, I send something to something. For example, T like something. We will see a few examples. Okay. And the verifier will send some challenge C0 and send another T2, T1, T2, and the verifier will also send the second challenge to me, and blah blah blah. I'll just a few rounds. So I send the final message to answer some challenge before to the verifier. The verifier now is convinced. Okay, you know that proof, but I don't know. But the verifier knows nothing about, except that I know that proof.
So
okay,
when you say probabilistic proof, basically that means there were so many challenges and all the challenges were proven correctly that with high probability and high chance, with like 99.99%.
Yeah, 99.9999 blah blah blah.
Okay.
Yeah. So it's a probabilistic proof.
So it's not 100%. It's not a it's not deterministic. Yeah. Okay.
Yeah, perfect. Perfect.
But when you are in zero-knowledge proof, where we never had 100%.
Yes, for sure.
Are always probabilistic proof.
Yes, if we just get rid of the zero-knowledge property, then the protocol can be reduced to the very round proof. Just the, how to say that in English? Okay, so can be transferred to the original mathematical proof. Actually, the mathematical proof is a subset of probabilistic proof. But here we got 100% soundness. Here the soundness, will be some small amount of soundness error inside.
Yeah, perhaps for engineers it's easy to see that in terms of computational feasibility, like
computational
feasibility, feasible. Feasibility.
Like it takes a lot of computation to maybe to send it back and forth.
Mm-hmm.
Yeah.
Is that feasible?
No, like a hash. Like you can see, like a hash. The fact that the preimage is also a probabilistic thing. No, there is a probability that I could fake a hash. No, like it's not 100% ever that I cannot have. So there is very unfeasible to create the hash without knowing the preimage, but it's not 100% impossible. No? So that's why it's the same. It's very unfeasible computationally to fake these T's without knowing the proof. It's very computationally unfeasible. Yeah.
But can you try like brute forcing to have a response that's closer to being correct instead of being incorrect, and I don't know, go through that hash?
It's the same way you could brute force a hash. You could brute force a hash, but it's like becomes computationally unfeasible because you need like all the computers in the world for 100 years. So it's the same here. Perhaps if you have all the computers in the world for 1,000 years, you could create a fake zero-knowledge proof, and that's like, I think, yeah.
Yeah, Leo are talking about something advanced. So I think I will explain that stuff kind of because for the zero proof there are different type of proofs. The one is called the proof. The other is called argument. If you see some articles online that some people mention argument, so what's the difference between argument and proof? So for argument, it's kind of a computational soundness. If a proof is a statistical soundness.
Yeah.
So it's different. Either we use proof or argument. But for some reason in the blockchain industry, we always use argument. Okay, I will explain why after today's session. We will to understand more and more advanced concepts. Okay. So far, any question? Is it clear? Okay. Fine. And okay. Let's next. Okay, it's an interaction, right? It's an interaction between prover and the verifier. So let's move on to, yeah. So there's another, so ZK and ZKP, right? Okay, here we got, now explain what the proof is. Actually, yeah, it is a proof. It is a proof, but an enlarged concept. But here, okay, what is zero knowledge? So I told you before that it is an adjective. It's an adjective to describe some proving systems, some active proving systems are zero knowledge, and some of those are not. For example, in the ZeroKnowledge lab, the teams, they always remove the zero knowledge part from their proving system to make sure the faster provers. So in the application of ZeroKnowledge and other, for example, ZKVM, the people don't care about privacy, they should remove the zero knowledge. So some people complain that, okay, when we talk about ZK, actually your system has no ZK property. So we will explain ZK property in details. But here we should know that, okay, zero knowledge kind of very important because from the 1985 paper that emphasized that zero knowledge kind of a very important property of a proving system. But it's okay to remove the zero knowledge property. It's okay if you don't care about the privacy. Okay. Now we move on to so some terminology that you will often hear or saw from an articles. Second is sorry, change the color. Number 2, ZK snark, ZK stark, NIZK, and blah blah blah. A few. Okay. Okay, ZK snark is a family of some ZKP proving system. It's a family of them. And stark now actually is a subset of ZK snark. So sometimes it's not so meaningful to compare those, I think a lot of people asking, okay, which one, this one is a snark or snark? Okay, actually snark is a snark, okay, because snark is academic word. It has a formal definition, and I think snark for starkware. Yeah, but always when we talking about the ZK-snark versus the story of ZK-snark versus ZK-stark, actually we compare KZG10 polynomial commits versus Frag polynomial commits. So we will talk about commits in following sessions. Today we just let's just clarify some basic concept, make sure the big picture view. In NIZK, if we remove the significance of proof, we'll get NIZK. If the protocol kind of has zero knowledge property and non-interaction, yeah, we call that proof as NIZK. Actually, there are many. Take a look into the academic papers written by photographers. A lot different destinations. So I think it's important to when we talk something concept, we have to have the formal definition in our minds to make sure that we are actually talking about the same thing. Okay, and yeah. Okay, for ZK-snark, there's some words that we frequently hear about is the circuits, right? Circuits. And for example, PCS And for example, the PIOP, very academic knowledge, PLP, circuit, PCS. Okay. Okay. What are this? Here I draw. I draw a picture of. Here. Okay, it's a proving system. We'll have 3 layers. Here with the proving system. Proving system. And then here we've got applications. Sorry, not applications. The particles built above the proving system. For example, decentralized storage or identity, decentralized identity system or ZeroKnowledge protocols built above the proving system. So there are also application level. For example, wallet or a website or the app built above the protocol. We can see that proving system kind of low level. There we have 2 or 3 layers inside. Generally, first is called arithmetization. Yeah, there. Here, this. Sorry. We got the circuit here. Circuit. And here we got PIOP, a pretty academic jargon. PIOP, or polynomial IOP, polynomial IOP. IOP is for interactive oracle protocol. And here is a PCS, polynomial commitment scheme. Okay, we got 3 layers. And here we still have some layers underneath the proving systems. We'll call them math. Yeah, but sometimes we can use math just as a black box. We just it's a library written by some geniuses. We'll trust them and call. If someone like me don't trust and verify, we will be very curious about how that works. So yeah, maybe we can talk about a little bit of math. Kind of very beautiful and interesting. And the circuit is here. So when we writing some circuit, we have to notice that the format of circuits has a very close relation to the proving system. So if we have 2 different proving systems, probably we have 2 different circuit, circuit formats or something. There are a couple of different circuit languages. I mean the formal language, not the programming language. For example, the RNCS. If any of you have any experiences of writing circuit.com, you are actually write the circuit in R1CS. It's called R1CS. So circuit, there's some R1CS, and another is Plonkish. And there's other more different, not so popular, but there are some.
Those are different. So ICS and Plonkish are different ways to implement the circuit, or
sorry?
Like ICS and Plonkish are different ways to implement the ZK circuit? Or?
Yes.
Okay.
They are similar, because the two circuits kind of we have two main type of gates, two types of gates, addition and multiplication. In RNCS, we always have the two types, just two types, addition and multiplication. But in Flemish, kind of we have can have customized gates. Means that we have a gate can do polynomial calculation just in one gate, or we can have some more powerful gates like lookup gates in Turkish, then more tabs gates. And also, for example, the air from the air is powder tool from the start with the tech stack. Air is very useful for ZKVM. For example, ZKVM or risk 0, so risk 5 ZKVM, something like that. Air is for the air is not a circuit. I mean, when we trying to encode or logic into or a piece of computation or function, we wrote them in air. Kind of we built a trace of computation. And just like a machine has a update, and we update the state, step for step. These errors were very useful for the ZKVM. Okay, the circuit. So today just show the picture. We don't go too deep.
Why do you think? Because I think it causes a lot of confusion to people to learn. What do you think we call them circuits? Because I think they are arithmetic expressions. No, they are in the end. They are the circuits are sets of arithmetic expressions. And I think it's easier for software engineer to see them as arithmetic expressions than think about them as circuits. So, what do you think we call them circuits?
A circuit. Okay. I think in the very beginning, so just the competitors were focusing on the theoretical part, saying how can we build a general purpose zero proof system for general computation. So it turns out that any computational or most of the computation problem or task can be reduced to circuit, arithmetic or Boolean circuit, the satisfaction problem. So it's a NPC, a non-deterministic polynomial Z-complete problem. So we can reduce. So if we build a snark or build a zero proof system for NPC problem, that means we can encode any NP problem, NP computational task into that. So a circuit here is a mathematical model. It's not a physical circuit.
Yes.
So it looks like a circuit with gates, but actually it's a mathematical model. It frequently used in computer science. For example, complexity theory. Yes. So I think why we got that the term. So today if we write the published circuit, we don't have any idea about it. We don't have to what the gate is. Just write the expressions as Leo said.
Yes. So this mathematical theory of NPC was using the term circuit already.
Sorry.
So the NPC mathematical theory was using the term circuit. Already, and that's why it got brought to the
Yes, correct. Okay, but this the architecture of proving system. I think there's a architecture proving system for nowadays ZK-snarks, not for all. For example, the Gross 16 has a different framework from this one. And that's because that I think the next session we can talk about the history of, we can see the very clear lines of work to see the YPCS, the programming equivalent scheme is very important in this. Today we don't go deep. And just remember this picture. And yeah. Okay, I think next topic I think yeah. Some people always ask me that they want to use ZK in their applications, and so how to quickly learn that ZK is for your goal or for your task. Here is ZKP if we're looking into the mathematical definition, it will be very confusing because it's far from your task. So here I introduce a very important analogy. Analogy, yeah. It's called the verifiable right? Commutation. Or it is often called the integrity or computational integrity. Computational integrity. Okay. I think it's an easy way to understand
Computation.
what are the proofs are, or what problem that the proof can solve. Okay, not 100%, but most of the time. Here we have two roles here, the prover and the verifier. So now me as a verifier, okay, this is me, a verifier. So now I have an intensive computational task. For example, to break a problem. For example, we trying to hash, computer hash to mine the Bitcoin, for example, a computational task. Here we have an intentional computing task. But I don't have enough computational resources. For example, I only have my mobile phone, so I cannot do that heavy computation. So I ask someone, the prover, so I delegate to the computer task to prover. So I also gave the prover's inputs, for example, a seed to compute hashes, input. Give the inputs to the prover. And the prover will, he probably has, a lot of machines can solve the problem and get the result, right? And send the result to me. Now the problem is how can I ensure that result is correct, because the computational task is run in remotely, right? And this guy, I don't know who he is. I didn't witness the whole process. How can I do? How can I ensure that result is correct? So it sounds an unbelievable task to how can I. So it's remote, remote machine. Okay, this is it's a very it's a good problem for a general proof. So for example, for ZK we don't trust the validator, right? We don't trust the producer, the code block producer. So we just we delegate the block of validation task to the validator, and if the validator can reply back the result along with the proofs, then we will just verify the proofs and trust. So it's a remote verifiable computation. The word kind of was popular 20 years ago because at that moment the cloud computing, the concept was very popular, and they claimed it will save the world. And so the cloud provider will want to provide the computation services to customers. So it's a verifiable computation, and some guy called the computational integrity. So they are same to concept same. The solution in there here is the prover proof that the result exactly the. For example, the task we use the F. So the prover will generate a proof pi, we call it pi, to prove that F of the X is the input, the equals to the result, the R, that is R, right? Result. So I think for many applications, if you think your task can be, some part of computation can happen remotely, and just let it happen, and ask the prover provide proofs. Okay.
I have a very dumb question.
Yeah.
Enlighten me. So like how can that there not be like front running the proofs? Front running the proof, like assuming I found the proof and I need to submit to the validator. If that process has transparency, how is that not front run by someone else?
Oh, it's a orthogonal question, orthogonal problem, because it's not a problem solved by the proofs. Kind of we have to use encryption or other cryptographic tools like command review, two phases, something like that.
Two phases.
Yeah.
Commit review. Okay.
Commit the proof first and then review the.
Okay, fair enough.
Yeah. I think the other approaches. Yeah. Any questions so far? No question? Okay. Let's move on to the next topic. Now we're trying to construct a very simple ZK proving system to say, okay, ZeroKnowledge proof kind of very intuitive instead of beautiful. Okay. The symbol is the example is classical. It's called the three coloring problem. Three coloring problem. Okay. So there's a fact that every two-dimensional map, there are some regions, some countries on the map. So we can always use the four colors to color each region to make sure every joint region has different colors. Okay. But can we use three colors? Only three colors to color in the map? Okay, that depends. Sometimes we will have a solution. Sometimes we don't, because just the map cannot color the best three colors. Okay, so three coloring is a NPC problem. So, for example, if we have a very large map with many regions on the map. So we have to reinforce every possible case to to find the solution. Okay, it means it's hard to find a solution. So this kind of information is called knowledge. Okay, as knowledge in zero knowledge proof. Okay, so we explained the proof before, and now we're trying to explain what knowledge is. Knowledge is a solution of some hard problem. So if I know the solution, you don't know that if I tell you, you got the solution, it equals to that you have more computational resources. Do you understand that? Even you don't have, but you got the solution. Equally, you have the same amount of computational resources to get the solution, right? So that information is not junk information. It's useful. It's so we call that kind of information as knowledge. So knowledge is a subset of information. Okay. So so that's why when we talk about zero knowledge proof, it does not mean that there are no information inside. It's just no knowledge inside. So if you see the zero knowledge proof, there's some 0, 1, 0, 1 bits, bit streams, but we cannot get the useful or your computational resources, worth something like that. The knowledge inside from the proofs. So for a zero knowledge proof, with zero knowledge property, the proof, it looks like it's just a randomness inside there. It just looks like the random. Okay, get the useful information, the knowledge from that. So the three coloring problem is that, okay, me now as a prover and you as a verifier, so I have a knowledge that, okay, you show me a map, I use my machines, a lot of machines to compute to get the result. Okay, this map is three colorable. So now I have the solution, but I don't want to tell you because it's valuable, right? But now I'm trying to convince you that, okay, this map is three colorable. It does has a solution. Okay, let me show that it's easy. Okay, it's easy. I just make sure everybody can follow. Okay, it's a simple, but you need to think it over to get the intuition behind. Three coloring problem. Now, as me as the prover, you as the verifier, there's a map. Okay, well, just for simplicity, just use 5 nodes. Each node represents the capital of a region. Okay. So we can have the edges between nodes. Seeing that, okay, the two regions are neighbors. For example, here, okay, we have we have 5 nodes. Okay, simple, right? It's simple. Now we have 3 cards. So as prover, I have to first of all, get the result of 3. Okay, here. Let me try. We use 3 cards. Red. Okay. Here is red. Here is blue. Here is blue to color this node. Each node for one region. And we use purple here. Okay. Now we can have a red for rightmost node, right? Yeah, it's correct. Okay, please verify. And for this, for this node, we have multiple choices. Just choose the blue one. Sorry, green color. Yeah, it is a solution, right? It's a correct solution. So the three-column problem is simple. It's a particle. It's an interaction between me and the prover and you and the verifier. So first of all, the prover will send the map to the verifier. So, but in order to protect the privacy, so I don't want to reveal any useful information about the coloring solution to the verifier because you don't pay me, right? So let me copy it. So we use we cover it by paper. I'll give you covered by papers, okay, to make sure you cannot see anything from the map. But I did. Sorry.
The screen.
Oh, sorry. Okay, the first step, I use pieces of paper to cover each node and give the map to you. So now you hold the map. I cannot change the color right now. Okay. The second step, as your round, is round for you to challenge one edge. Yeah. Which one? Anybody select one edge?
You can mark the edges and we can choose.
So, okay. Which one?
Like you can mark the edges with numbers and we can choose randomly.
Yes, you can choose that one just randomly because
Like
it's
the blue one.
blue one. Okay, blue. Blue one. Okay. What about this? Okay, this edge. Okay.
Yeah.
Because I am an honest prover, so I don't afraid of showing the edge to you. So I suppose I just discover that. Okay, discover. Yeah, you're satisfied, right? Oh, okay, sorry. Sorry. So I revealed two nodes to you, so you check. Okay, if the two colors are different, I'll use the same one, right? So my question is right now, so are you convinced?
No.
No.
No, right? Because probably I'm so lucky.
Yeah.
Because now we have 1, 2, 3, 4, 5, 6. We have 6 edges. We only verify just one. So only 1/6 possibility that I am honest. So you cannot be convinced. So, but I cannot let you challenge the second edge. Otherwise, you will get the solution.
Yes.
So I only allow you to just check one edge. Yeah. Okay, the third step. So in the third step, I'll just copy that here. So next step for me is to permute that, do a permutation over the colors randomly. For example, So I do a permutation of 3 colors. All green color change to the red color. And the red colors change to purple. And the purple color will be changed to green, right? So I will again coloring the map. So here, okay, because this node is red, so red will be changing to purple. So here we color this node purple. And for this node, green to red. So I color this red. Okay. For here, it's red into purple. Yeah, I do the color is purple. And here is purple into green. Into green. Here is green to red. Now, I use the paper to cover every node to make sure I cannot see the solution. Okay, the US reference. Okay. Pick one of those.
Yeah.
Green. The green, okay. The vertical one or this one? Vertical, okay. Remove the cover, okay. Yeah, because I'm honest, okay, you'll find nothing special. Okay, the 2 colors are different. The purple and the green. Okay, now are you convinced?
Not you.
No, right? It's not enough.
Yeah.
Yes. Okay. We have already 4 rounds, right? But it's not enough. You can do it, okay, repeatedly until that you are convinced.
Yeah.
Probably 1,000 rounds, probably. Okay, until you get some probability that the possibility is that each time I have the 1 minus 1/6 to escape your check. Then after T round, we'll get possibility that that I have the knowledge, I have the solution. Okay, it's nice here. So, okay, good news. Okay, that's the particle. It's pretty simple, right? The model is smart, and the idea is similar. It's quite similar. We can see some very important ingredients here. The first one is the verifier can randomly challenge. The challenge cannot be predicted by the program. Otherwise, the program will be very easy to cheat the verifier. So the verifier has to, just randomly, or use your strategy to make sure that you okay, you try hard to find the cheat of the program. Okay, the first ingredient is random challenge. So for a very, for almost all the XNAR we use today, there are somewhere there the verifier will check, randomly check. For some protocols, the verifier just do 1 check. For some of the other, proving system, the verifier have to check a lot. So the more challenges, the bigger the proof is. That's why Stark has bigger proof. Because in Stark protocol, the verifier has to check more often. But in for example, group 16, the verifier just verify only once. It's a elliptic curve based Stark. So elliptic curve provides some tools that are very easy.
You just mentioned the Stark, the proof size is larger because there are more verification steps. The verifier asks for more. So the proof is larger because you need a larger set of information that the verifier can check. That's the reason, or why is the proof larger?
Okay, two factors. One is the interaction is more wrong. Logarithmic of size of statement. Logarithmic. And for each round, because all the information committed by a Merkle tree, so the Merkle path is another logarithmic size of the problem. So we got the logarithmic square size of proof. Okay. The first important ingredient is the random challenge verifier. So here is a problem. So today we use XNAR is kind of so-called non-interactive proving system. So no interaction at all. So it's kind of confused, right? We need the verifier online to challenge, but also we need the proof kind of used in synchronized the blockchain world. We need the proof. Once the proof is generated, that proof can be transferred to anyone, or put it on chain, be verified a few days later, or even 100 years later. So how can we do that? So we have to use. Okay, this stuff is about computer science, not cryptography. Now we'll have to use the tool from cryptographers. I'll use some tool to transfer that interactive protocol into non-interactive protocol. Yeah, that's okay.
Question.
Ah.
Right now with like the exchanges and showing the different data, we're challenging you to prove that you solved the entire thing at once. Like you have the solution for all the three colors.
Yeah.
But that's in one proof.
Yeah.
Couldn't you just make 5 proofs for each node showing that no node is touching another color? And then you've proven that every node has been solved, but without revealing the information about everything.
Yeah. Yes.
You could also do it that way. 5 proofs instead of 1 proof about everything.
Sorry, ask your question.
So because we have 5 nodes, the challenge is to, or the puzzle is to like find a way that each node isn't touching other nodes, or other colors. Couldn't we just generate 5 proofs for each node, showing that every node has been solved individually, but not showing the complete answer, instead of having 1 proof that shows the entire solution of everything?
Yeah, if you do that, the verifier will get the solution.
You will have the knowledge.
For each proof, you will reveal something useful, or reveal part of the knowledge to the verifier. The verifier will get more proofs, and eventually the verifier will adopt the knowledge. That's what we want.
Question.
Okay.
We think with this protocol, for sure, the verifier cannot get the solution if you go enough rounds.
Yes.
I have the impression if you do all the vertexes, you reveal all the vertexes, the verifier could guess, the solution.
No, because for each round, the verifier, the prover always put randomness into the solution. So
yes.
The verifier cannot get anything. So I think next session or next session we'll see how do the security analysis to prove that actually this protocol does not reveal anything about the solution. We can prove that. Yeah. Problem today. Yeah.
Is it computationally heavy to generate these permutations of the solution? Isn't that like getting 5 different solutions is it the same or as 5 permutations of a solution, or is it heavier?
Sorry, can you repeat your question? sorry for my English.
Is it computationally heavy to generate these permutations around a solution? Is it not like having 5 different solutions, for example, in this case?
Mm-hmm.
How hard is it computation for the?
The permutation part is very easy. It's just randomly because we only 3 colors, so we have just a few.
It's constant, no? It's constant time or just like
constant. Yes.
So the validator, the verifier doesn't care about the colors themselves, but more of the vertices and the quantity of which one of them are connected to each other's.
Yes.
Okay.
Yes. So there's something that I have to mention that because this map is so small, because the map is so small, so the verifier can compute the solution by himself. Yeah. So zero-knowledge proof is meaningful if the map is huge. So that's a problem, very important problem. So otherwise, zero-knowledge proof is kind of useless. So make sure that the knowledge is exactly knowledge, not some cheap information can be easily obtained by the verifier.
Can we see what we are missing also, like when the prover sends one of the permutations? I guess it's like a commitment before the verifier asks which one to reveal, no?
Yes. You're correct. Yeah, thank you, correct. The second important ingredient. Thank you. Is that how can I use the piece of paper's cover is no. How can I do that in program, right, rather than code? So the cryptographic tool will provide some protocol called commitment scheme. So we can cover that. The cover is just like a metaphor. I don't know how to say it in English.
Metaphor, yeah.
A metaphor?
Is a metaphor or analogy. Some people are very big and say, no, it's not a metaphor, it's an analogy. They say, oh, you are being very pedantic.
Okay, so let's explain more that how can we transfer this kind of protocol into using code and program language. So how can I use the paper cover is So we can see for example, this is a solution. We use the capital S as a solution of this current, and we use the notation like square brackets S as a commitment. Here we have actually multiple choices. How can we construct a commitment of S? First of all, we use a hash, right? Hash S. We got the hash value of S. I send the hash to verifier. Also, we can use the Merkle tree. If S is a big vector, a big array, so we can use the Merkle tree. Or we can use something called the Peterson commitment. It's a elliptic curve. Elliptic curve. Or we can use PZG10 commitment, polynomial commitment, something like that. We can commit that. So for stock, we use a Merkle tree. For Plum, we use PZG10. There's some proofs and use of Prism. For example, the bulletproof and some. But there
When you put the hash, it's not like a normal hash, no? Because a normal hash, you need to know all the input. the one you put.
Yeah, we can use a hash because the S is small. Yeah.
But if you use like a normal hash, what we understand for a hash, to check the hash, to check the commitment, you need to know all the information. No?
Yeah, yes.
So then you would reveal everything, no?
Yeah, yes. Yes, hash is okay, sometimes useful, but always we don't use hash because hash.
So I mean, in this case, in the case of the coloring.
Yeah, yes. I think that for the hash. Yeah, so probably we should use small tree here.
Yeah.
Yes, yeah, you are correct. Yeah.
You think there's going to be a lot of changes in circuits in ZKP if we implement the vertical tree, or we can?
Yeah, we can use vertical tree here. Sure. A vertical tree is built up on ZK10.
Yes.
Yeah, we can use that. Yeah.
Yeah, but the commitment scheme that you use in blockchain doesn't have to be related to the commitment scheme that you are using the zero knowledge. It can be independent, no? So you like if we implement vertical trees in Ethereum, is unrelated if we use vertical trees in
Yes.
in this
That's
case.
the question.
Yes, so it can be different in one place and another.
Okay, the last topic today, the random Morocco, and the Shamir transform. Okay, random Oracle Fiat-Shamir transform is used for transfer the interactive particle into non-interactive particles. It's very useful, very useful. The idea is that because in blockchain we cannot use interactive, most of the cases we cannot use interactive particles because the bandwidth is kind of expensive. And we need to put the proof on chain. So verify later by the validators, repeatedly verify by validators. So for some proofs that can be easily to be transferred to non-interactive particles. Okay, there's a characteristics about those particles that all the message sent by verifiers are random numbers. For this example, so all the message from the verifier to prover are random numbers. So that means we can, for example, we have prover, verifier. Now we introduce another angel here in the sky. So the prover can interact with the angel to complete the whole particle. Because there's multiple rounds, right? For example, 1,000 rounds with the angel.
Angel? How is it written?
The angel.
The angel will be replaced with the hash function. Then, so just imagine
Let's
here
press
you
it
have angel here. We just assume, and
Like
then
third
we
party.
can realize the angel using cryptographic proof. Okay, is that clear? Okay, good. So now, if we introduce the angel, we talk with me as a prover. I'll just talk to the angel to complete. Sorry. To complete the interaction. The angel, all the work that the angel just send to the random numbers. So the angel don't have to be, understand what the particle is. Just the angel just, stupidly, send the random message. So the prover, after the interaction, the prover can pack the transcripts, all interactions with the angel, and put into a box and send to the interaction here, interaction. And send to the verifier. The verifier will check the interaction is correct or not. So now the protocol has been transferred into just one round protocol with the verifier. So now, how can I build the angel? So we just use a secure hash function as the angel to complete that interaction. So the hash function will, for example, and write down the original protocol T1 and C1, T2 and C2. Here we just remove the angel. It's a hash function. Though the angel can compute that C1 equals to hash T1 plus other context information. For example, today's the weather, some other randomness or which blockchain we use, and some name of this protocol to prevent the rerun or the.
Can we move the screen again? So we can.
Sorry?
The screen.
Oh, okay, sorry. And the angel gets C2, compute the C2 by hash C1 plus T2 to get the C2. Okay. Blah blah blah.
Is in this case not the angel the verifier?
The angel is not verifier. The angel is a hash function. So prover can use a hash function computed by the prover. Prover just uses a hash function to generate the transcript.
But I thought the transcript is all the steps, all the challenges. Is that not the transcript? What is the transcript? Can we?
Yes. Yeah. Challenges are part of.
Right. But shouldn't the verifier make all the challenges, not the angel, in order to create the transcript?
Can it be like the key feature of the angel is that the prover cannot control the angel? No?
Yeah.
The key feature for security of the angel is the prover cannot control the angel.
But the does the verifier interact with the does the verifier interact with the angel? Because
yes, it has to be something that the verifier can verify at the end. No? But the angel has been computed correctly, but the prover cannot cheat, they cannot decide how the angel works.
The verifier is providing the inputs, right? T that's going into the angel.
Sorry?
The verifier is providing T, which is the input into the angel, right?
Oh, okay. Yes.
The verifier is always the one supplying it. Anyway.
Yes.
Okay, so
angel. Yeah, angel now is a hash function. Can be realized as a hash function. So prover will use a hash function to generate the whole transcript. And the verifier got the transcript. The verifier also, use the hash function, the angel, to check if the average challenge number is actually.
Okay, I understand. But my point is that if all the verifier gets is the transcript, right? All the verification, all the checks, all the challenges are in the transcript, right?
Yeah.
That kind of means all the challenges have already been done by the angel, but actually the T comes from the verifier. Like if all the verifier gets is the transcript, the verifier didn't randomly decide on the challenges.
It is computationally unfeasible to calculate a T1 that as there's so many challenges you can, because you need to inverse the hashes. If you want to get to lie to the verifier, you need to inverse all those hashes to kind of calculate the T1 that gets you to the result that you want. So the prover couldn't create a T1 that gets to where it wants to go. You know what I mean?
So the angel already sent its hashing. He already sent it hashing.
No, the engine is a hash function.
Is it? Okay.
Yes.
Right.
I don't know, I just feel like the transcript, like the way the transcript is generated is not clear to me. Like how is the transcript generated? Is it still the interaction between the prover and the verifier?
No, it's just done by the prover.
Yeah, but okay, so
himself.
by himself.
Yeah.
Yeah, okay, but that doesn't make any sense to me. Like why can the prover create the transcript himself?
Okay, yeah. Here's the point. Okay. The only way of cheating, I mean, for the prover, so if a prover can predict the randomness, the prover then can cheat.
Yeah.
So by using a hash function, because a hash function is a one-way function, you cannot compute the pre-image through an image, right, with the image. So if we put the T1 into a hash function, we got C1 by the prover. So because the hash is a one-way function, so if the prover wants to modify T1, the C1 will change with the T1.
Okay, so if we go up to the free coloring problem,
Yeah.
actually, or even the input, it doesn't really matter. Like the input is provided actually by the prover.
Yeah.
But because we use an angel, the input is random, so it doesn't even matter if who provides it in the end.
Yeah.
Okay, then it makes
Yeah.
okay.
Yes. So I think yes. If we know that the security analysis of this protocol actually is we're talking about how a prover can attack the protocol. The very important key of attacking is that prover predict the randomness. So the hash function will prevent prover from prediction. So even the hash function is transparent at all. So even the prover will get the randomness. The prover can, according to the randomness, and go back to the first round to change T1. But it cannot because hash function is one function.
Okay, but in this case, it's actually not an interaction really. Like it's not really an interaction between the prover and the verifier.
Yeah, it's just the prover can do it by
himself. Okay. Yeah.
So precisely the point is to make interactive protocols into non-interactive protocols. This is used for that.
Yeah.
So that's the actual goal. Yeah.
To make it feasible because you cannot really, to make it like easy. Then you just send this transcript, the hash transcript on the blockchain, and you just.
That's the proof. Yeah, that's the proof.
Yeah.
Do you have an example of like applications that would use the random oracles for to prove something? Because in my mind, when we're proving something, you have to make sure about the inputs you're submitting. So why would I be using randomness to try to verify something?
Sorry. Your question?
I feel like I would use ZK for something that is more that try to be more precise as possible.
Mm-hmm.
So why would I have to use randomness as a source of input?
Okay, for the input, right?
Yes.
For the prover, put the randomness in the input, right?
Yeah. Let's say I have a theorem like A plus B equals C. If I want to have the correct answer, assuming I'm the prover that knows the answer.
Yeah.
Like I know my A equals 5, so there's no point in trying to submit like random numbers because I know it's 5. So when would I need to use the randomness? Which is a situation?
Okay, there are two randomness here in the protocol. The one is that the randomness generated by the verifier or the angel trying to trying to catch the dishonest prover. And another randomness in this protocol is from the prover. The prover wants to protect his solution, protect the privacy. So for each round, the prover will mix some randomness into the message sent to the verifier. So before sent to the verifier, the prover will put some randomness each round into the message. Make sure that the transfer with all the messages sent by the prover looks like random.
Okay.
To make sure that they are knowledge property. to protect the privacy. If you don't care about privacy, the prover don't have to put any anything.
Yeah.
All right. Nice, thanks.
Yeah.
And this transcript is then also probably hashed again, and then actually that's being then put on chain, or what happens once everything is actually done? Like what happens with the transcript then once it's like the prover sends the transcript to the verifier?
Yeah.
And then what? The verifier.
The verifier will replay the transcript to
Right.
make sure the C1, C2 to
Correct.
CN are correctly computed by the hash. So yeah, that's why the more interactions, more gas consumed on chain, for example, on Ethereum. Yeah, it's almost okay, 2.5 hours.
Yeah.
It's
2.5? 1 hour.
Oh, sorry. 1.5 hours. 20 minutes.
Yeah.
Your laptop time is 1 hour. I don't know. It shows 4:22. We have 3:20.
It's just a
Yes, you're
Chinese
doing
time.
China time. You're in China time.
Chinese time zone. Sorry. Okay, I think it's enough today.
Yeah.
And,
ขอบคุณครับขอบคุณครับ
yeah, so if any question is
Automation to show for the 3 color problem. Can you show now?
sure.
Sure.
Like I have an automation. Like he like he told us about the 3 coloring. Like I have an automation which I can show how it works.
Yes, but
Like a visualization.
now or next time? I don't know if it's too
It's
late.
just a visualization.
Sure.
Like an example for the free
Yeah,
color.
Yeah, okay.
Sure. Yeah. You record it also, yes.
I just have the automation. Oh, I'll do the connector.
Yeah.
So actually, like as usual, like we have 2 graphs. Like this graph is like 3 colorable solvable, and we have graph 2, and like this one is not solvable. So like we'll try to run proof and verification to see if it is correct or not. So like if we choose graph 1, and right now we have 0% confidence that it is correct. So like we can choose any random edge, say this one, and we see that it has like different colors on both the nodes. So our confidence is 6.67% right now. We'll choose like if we choose the another node, say this one, we see that it has like different colors, and we can choose again this node, but we will not be able to see the colors because the prover has applied some randomness here. So yeah, the colors are different, but it still has like different colors on both the nodes.
Right.
So like now the confidence is 18.7%, and
So 3 checks.
yeah, like so instead of doing it manually, if I like run into the turbo mode, so like it will randomly choose all the edges, and our confidence just keeps growing. So like this, once it reaches a very high confidence, we know that it is 3 color solvable. So like yeah, like 99.99 something, like it will keep on running, but it will never be like wrong because it is solvable. And if we are getting zero knowledge about what the colors of the graph So like this one is the solvable part, and when we see the graph too, so if we try to manually find out that if it is solvable or not, so like we can do that. Maybe this one, like we get the confidence, yeah, it is correct. Then this one, but like confidence is increasing right now. So we might think that yeah, this graph is solvable, but once we run into the turbo mode, we find a edge which has two same colors. So like this is not solvable. If you like, if that's so like this is what he was explaining actually. Yeah. Like we
Can you say again why it's not solvable again?
like this graph cannot have like all the nodes with different colors, so it is not solvable. So like we can prove that. Maybe if we run again, say like the turbo mode, yeah, we find again. Yeah. So
You can send the website in
yeah,
Discord.
sure. So like I had the confirmation, so this is
Nice. Very cool.
Great.